Our next up, Vipul Sabhaya from HP. He's going to talk a little bit about how this fits into a public cloud environment with a few servers, I think you got it.
Yeah.
Thanks, Vipul.
Hello, my name is Vipul Sabhaya. I work for HP Cloud. I've been with HP for about 2 years. When I started HP, I was sort of given the task of figuring out database as a service for it to provide as a public offering. Initially, we started, with a Java application. We did the whole thing, and then, we had something that we ran in beta. Soon after that, I talked to some of the guys at Rackspace. It sounded like they were working on something similar, and that was called Red Dwarf at the time. We joined forces. We're, I think, the second company to get on board with Trove, and right now we have it in production in our public cloud. We have many customers actually using Trove. So hopefully this talk, so what I'm going to talk about is Trove, how to deploy Trove in an HA mode, how we do configuration management, some of the monitoring things that we're doing with Trove, and how we actually operate Trove. Hopefully I'm not stepping too much on what Austin just talked about, so hopefully it's not a complete repeat here. So Trove, you've probably seen this many times today. Trove's database service, MySQL, MongoDB, Cassandra, Postgres. We're an integrated project. Some of the architecture. So Trove is composed of essentially 4 major components: the API, the conductor, the task manager, and the guest agent. There's also data store specific images that live in Glance, so Trove knows how to boot a specific type of data store. Connecting all this is a RabbitMQ cluster, or a RabbitMQ server, and a database. So which cloud do we deploy Trove into? And I think when Austin talked, it sounded like they're actually deploying this on bare metal using Puppet. So Trove actually only has API dependencies. It's completely independent of other OpenStack services. So we have the option of deploying it on bare metal or the over cloud in OOO terms, or we can deploy it in cloud. That's actually how HP is deploying it. The entirety of the Trove control plane runs in VMs. So I'll go into depth a little bit on that. So how do we get HA within Trove? To really get HA, you have to have HA in your over cloud. By over cloud, I mean your OpenStack, Nova services. Those actually have to be HA, and there needs to be some concept of some physical as well as logical separation of assets. So in HP, we run OpenStack with availability zones. These are actually physically separated within a single data center. They're logically separated using Nova aggregates. The Trove control plane, we run the control plane across the availability zones that are supported by the underlying infrastructure. We use a Galera cluster, one node on each availability zone, so we have 3 AZs. We use a RabbitMQ cluster with mirrored queues, exactly like what eBay is running. And each node of the RabbitMQ cluster is also in a separate AZ. We run multiples of the API, all the Trove services, so we have multiple APIs, multiple task managers, and multiple conductors. What this kind of gives us is the ability to lose an entire AZ and still have Trove up and running. If we lose 2 AZs, then Galera shuts down. So, at a very detailed level, this is what our deployment looks like. If you can't see this, the things in the right here in blue is our OpenStack infrastructure. So, and each box represents an AZ. Within an AZ, we have a head node, or a number of head nodes that contain the Nova and Cinder and Glance processes. Across the 3 head nodes, we have the RabbitMQ and Galera clusters that are talking to one another within that data center. If we move to the left a little bit, that's where our Nova compute nodes live. And within those compute nodes, we spin up VMs within each AZ and run the Trove control plane. And within the in-cloud VMs, we also run a separate Galera as well as RabbitMQ cluster. So at the end of the day, what we have is a private OpenStack deployment that's HA and the only endpoint visible to the end user is the Trove API endpoint. Because of this, we don't have actually the same problem that Austin talked about, where they see instances in the Instances tab as well as the Trove tab. The Instances tab doesn't exist within this deployment, since the endpoint is not visible. So how do we get to that picture? We rely heavily on SaltStack. The entirety of the Trove deployment, as well as our cross-AZ OpenStack deployment, is based on SaltStack. And actually, the code is available publicly for most of the stuff. So what do we use Salt for? For config management. It helps us define sort of the packages, the dependencies, and the various things that need to be installed on these VMs. We actually also use SaltStacks to copy configuration files with the right content to the target VMs. We also manage users, groups, policies within the actual operating system using Salt. This allows us to sort of have a reproducible state of the infrastructure. So if a VM dies, if one of our Trove API VM dies, it's a simple Nova boot, and we're back up. And we also use Salt in the guest instances. So we have a Salt minion running on every Trove instance that's spun up. And the first thing it does is it does a high state against the Salt master and gets all the configuration it needs. We also use Salt for remote execution. So the Trove instances themselves, we turn off SSH. Our control plane instances, we turn off SSH. So we don't allow anybody to log into anything within the entirety of the Trove deployment. We do allow you to log into the Salt master. And so we have an HA setup of Salt master and a Salt slave. And essentially, we can control the infrastructure from that one machine. We manage sort of the access levels within that Salt master. So certain users that log in can perform some operations. Other users can only perform other operations. And it's very useful also for managing, we have hundreds of thousands of customer instances. Salt helps us run commands on customer instances if we need to. So if the guest agent process is in a weird state, or if some disk issue has happened, we can successfully run and fix those issues from one place, essentially. In terms of what a state file looks like, what a Salt state file looks like, this is just a snippet of the Trove API state. We're sort of declaratively saying to install a certain number of things, like packages, copy a certain file to a location on the target machine. It's all YAML, and I think these examples, as well as they're also open sourced in that repository that I mentioned. And the other side, so the SLS file, if we go here, we're telling it to copy a certain configuration file. The configuration file looks like this. It's essentially a template that Salt can replace values in. And we can configure things like where the guest agent should talk to RabbitMQ at, and what the credentials for that RabbitMQ server are. And so that was kind of our public cloud. I'm going to shift a little bit just for this slide, actually, and talk about what we're doing with Helion. So HP's got a OpenStack distribution called Helion. We're actually running Trove, or we're shipping Trove within that distribution. We've decided to go away from Salt and kind of be consistent with the rest of Helion. And that really is based around image-based deployments. So the concepts of O, which is, I don't know if you guys are familiar, but it's essentially using OpenStack to deploy OpenStack. So where you have essentially a bare metal, so instead of provisioning a VM and booting a KVM VM, what we do is we swap out the driver so that I can do a PXE boot of a bare metal machine. So that concept allows you to essentially use a Nova that's configured with that specific driver to lay out an image on a bare metal machine. Where Trove fits in is using Heat, as well as the images, disk image builder, to create a deployment and have it configured through Heat and sort of orchestrated through Heat. And essentially what you end up with is a control plane that's exactly like what we had with Salt, but done through Heat and OOO. So the concepts of using Salt Cloud or an overwrapper, and you have a Salt master, and then you get Trove, changes to you go have a seed cloud, you create the under cloud, which creates the over cloud. The over cloud is the cloud that your customers would want to interact with. That's the endpoint that a customer would use. We use Heat in the over cloud and essentially have a Trove deployment that's completely virtual. So shifting back to some of the operations stuff that we're doing with SaltStack. So all of our operations are based on SaltStack. We have, I think I mentioned this, but we have an HA deployment of the Salt masters. There's a master slave. The configuration is completely synced using rsync, and I think it's like every 5 minutes we copy the key from the master to the slave. We control access to infrastructure with SaltStack. We also control access to customer instances. We don't want to log into a customer instance if we don't have to, but if, in case we have to go and debug issues, this helps us do that. And each Trove guest becomes a minion, so we have a special image that we create for production, and that image contains MySQL as well as the guest agent software as well as a Salt minion package. Upgrades, I think Austin and eBay touched on this a little bit. Austin and Matt, sorry. Trove, so one of the things that's challenging with upgrading Trove is the data store. The customer instance must be usable during the entirety of the upgrade. We can't bring that down. Upgrades currently, in its current form, usually involve downtime. And by downtime, I mean not of the customer instance, of the Trove control plane. So we're working on fixing some of those things by introducing RPC versioning. There's some patches up to do some of that. And the upgrade sequence, this is what Austin and Matt also talked about. We upgrade the guest agents first, and then you go jump up and you upgrade your task manager, and the last thing you want to upgrade is the API servers. The reason for doing this is if a new RPC message or method is introduced, it needs to be available at the very low level before an API operation can be performed. So in terms of security, we're using SSL across the board, basically, on the API nodes, on RabbitMQ. We don't do SSL on the database. Security groups, since we're deployed completely in cloud, we can leverage Nova and Neutron security groups to sort of restrict access to these VMs. So for the service database, we've set it up so that only the control plane can actually communicate via 3306. For RabbitMQ, again, we've set it up so that only the guest agents, as well as the control plane, can talk to it. And we're expanding on this a little bit in Helion, where we're using Neutron. We're actually going to be designing a separate network within Neutron so that there's a network for the control plane and an independent network that has RabbitMQ and the guest agents. So there isn't much visibility. I mean, the only thing that the guest agents can talk to would be RabbitMQ at that point. The other important point is to use separate credentials for each service. This allows you to rotate passwords and those things more effectively. Monitoring. So Trove doesn't ship with monitoring. Nothing in OpenStack ships with monitoring. So a lot of this is left up to the end user, the end deployer of the service. So some of the things we've done, we have Upstart. We use Upstart for everything. We set it up to respawn the service in the event that it goes down. We use Nagios to monitor ports. We also set up monitoring within the control plane so that we're pinging and checking that we can connect to RabbitMQ and the database from the other control plane nodes. Some of the things that you probably want to monitor in terms of RabbitMQ, there's a bunch of things you can look at, but number of queues, number of sockets, established connections, periodically checking the cluster status, and monitoring whether, in the log file, whether there's any failed attempts to access the server. In terms of database, we're using standard MySQL packages for Nagios to monitor, the standard things. We built a check to Nagios to do a check of the Galera cluster. So we're always checking to see that there are 3 nodes in the cluster. We're monitoring the slow query log for anything that's greater than a second, the error log for authorized attempts. In terms of Trove, what to monitor, so one of the things that we've noticed running many instances is the heartbeat of these instances isn't quite accurate all the time. One thing that you may want to do is to set up some sort of a job or something that keeps checking the heartbeats table and notifying you that there's a failed heartbeat or a heartbeat that's not a success. We've attempted to do that by creating this trigger. Essentially, whenever there's a record that gets updated on the instances table, we write a record in another table. So whenever there's a record that gets updated with a certain status, like a failed status or something like that, then we keep track of that instance in another table. That allows us essentially to go back, when we're all at work and look at the instances that may have sent a failed status and figure out why that happened. We also monitor, since we've got multiple regions at HP Cloud, we also have a monitoring server that lives in a different region. So we deployed Trove in East and West, and we have a server in East that monitors connectivity to databases in West, just to make sure that there's cross-region connectivity. So I'll touch on some of the things that we've learned doing this for a few years now. RabbitMQ is kind of our biggest pain. And some of the things that we ran into, some of the things that we've changed are to update the default descriptor limit. You have to do that pretty quickly, otherwise RabbitMQ will just die. One of the biggest issues that we ran into was the number of queues and sockets on a RabbitMQ server will just keep growing infinitely. And there was a patch in Oslo to enable heartbeats on a RabbitMQ connection. That patch, for whatever reason, wasn't accepted. So we've had to extend the Oslo Kombu implementation so that we're sending a heartbeat every 20 seconds or something. And if that heartbeat is not received, then RabbitMQ will actually kill and close that socket. So that's kind of a big thing that we've had to do. The red alert is kind of interesting because we're running RabbitMQ in a cluster mode with mirrored queues, and we're running it in cloud. So we're kind of prone to network partitions. We're going to have cases where the network just dies across an AZ, and RabbitMQ isn't quite meant for that. On their website, they've actually put this where they're saying don't run clusters in scenarios where there's network partitions. So that's probably one of the reasons why we're having such a hard time with RabbitMQ. So guest agent heartbeats. I think we touched on this a little bit, but we monitor that for failure. Upgrading the guest agent on the extra small instances has been challenging due to some of the memory limitations. So it fails more often than it succeeds. A lot of times we have to go and manually shut some things down so that we have enough memory to do an upgrade. And I think this is we should have shared notes, Austin. The quota mismatch, yeah, that's one of the biggest issues as well. Austin already talked about this, but where Nova thinks that there's a different set of usage compared to Trove. We've written some jobs to sort of go through and look at both tables, I guess. We look at the Nova table to see how many, what the quota is and what the usage is, and we look at the Trove tables, and we kind of just adjust them on the fly. And that's it. Cool. Thank you.
Thank you, Vipul. Appreciate it.